Artificial intelligence. Two words that, in 2025, appear in almost every conversation about the future. Every company has a strategy for it. Every government has a policy about it. Every newspaper runs stories about what it might do, is doing, will do, cannot do, should not do. And almost no one, when they use those words, means the same thing. For some people, artificial intelligence is ChatGPT, the thing you type questions into and get answers from. For others, it is the algorithm that decides which posts you see on social media, which loan applications get approved, which faces a surveillance system flags. For others, it is a future technology, something not yet here, but coming. A mind in a machine. For still others, and this is a smaller but not negligible group, artificial intelligence is a threat. Not a metaphorical threat, an existential one. The thing that might, if not handled carefully, end the human era. All of these people are talking about different things. All of them, in their own way, are partly right. And almost all of them have a history of artificial intelligence that begins around 2016, or 2022, or perhaps as far back as the 1990s, if they are historically inclined.
The actual history of artificial intelligence
Begins in 1936, with a man on a bicycle riding through a field in England, watching mechanical arms drop small metal balls to demonstrate a calculation. Actually, it begins earlier than that. It begins with the question that every civilization that has ever thought carefully about the mind has eventually asked: can a machine think? The idea of an artificial mind is older than computers, older than the word machine in the modern sense. It is in some form one of the oldest ideas in human culture. Greek mythology described Talos, a giant bronze automaton built by the god Hephaestus to protect the island of Crete, animated by divine ichor running through a single vein. The medieval golem, the clay figure brought to life by a rabbi through the inscription of the sacred word, was a servant, a protector, and a being that could not be trusted with full autonomy. Medieval and Renaissance automatons, mechanical birds that sang, mechanical knights that could stand and bow, were marvels that raised always the question of where the boundary between mechanism and life actually ran. These were not scientific proposals. They were myths, legends, thought experiments expressed in the language available to their time. But they were asking the same question that computer scientists would eventually ask in formal mathematical terms. Can something we build think? And if it can, what does that mean for what thinking is? The person who first asked that question in a way that led directly to the technology we have today was a mathematician who rode a bicycle through the English countryside, worked in a converted Victorian house during the war, and was destroyed by the government he had served. He is the beginning of this story, but he is not the only name in it. Alan Turing, as we discussed in the episode on the first computer, published a paper in 1936 called On Computable Numbers with an Application to the Entscheidungsproblem. The paper solved a problem in mathematical logic by inventing a theoretical machine. But embedded in that paper, and developed further in subsequent work, was something more than a solution to a mathematical problem. It was a theory of mind. The Turing machine, the idealized computing device Turing described, could, in principle, simulate any computational process. Any process that could be described by a finite set of rules could be executed by a Turing machine. This is what computer scientists mean when they say that modern computers are Turing complete. They can, in principle, compute anything computable. The implication Turing drew from this, carefully, speculatively, was that if thinking could be described as a computational process, then a Turing machine could think, or at least could simulate thinking. And if the simulation was indistinguishable from the real thing, what was the difference? In 1950, 4 years before his death, Turing published the paper that introduced this question to the world. Computing Machinery and Intelligence opened with the line, "I propose to consider the question, can machines think?" He immediately acknowledged that the question was too imprecise to be answered as stated, so he replaced it with what he called the imitation game. A person sits at a terminal. They exchange text messages with two entities in another room, one human, one machine. If the person cannot reliably determine which is which, the machine has passed the test. Turing was not claiming that passing this test meant the machine was conscious, or felt anything, or had any inner experience. He was making a more precise claim, that the question of whether a machine could think was operationally equivalent to the question of whether its behavior was indistinguishable from that of a thinking being. Whether that equivalence is philosophically satisfying is a question that has been debated for 75 years. What is not debated is that Turing's paper defined the terms of the debate that artificial intelligence has been having ever since. In the summer of 1956, a group of scientists gathered at Dartmouth College in Hanover, New Hampshire, for a workshop organized by a young mathematician named John McCarthy. McCarthy had written, with Marvin Minsky, Claude Shannon, and Nathaniel Rochester, a proposal for the workshop. The proposal contained a sentence that created a field. "We propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College." The phrase, artificial intelligence. Two words joined together for the first time in an official scientific context. McCarthy coined it specifically because he wanted a term that was distinct from automata theory, cybernetics, and the other competing descriptions of the same general enterprise. He wanted a clean name for a new field. He got one. The name stuck. And for better and for worse, it has shaped how people have thought about the project ever since. The Dartmouth workshop did not produce the breakthroughs that the organizers had hoped for. The 2 months turned out to be wildly optimistic. The problems turned out to be harder than anyone had anticipated. But the workshop established a community, a network of researchers who now shared a name for what they were doing, a set of common problems, and a mutual ambition. McCarthy went on to invent Lisp, one of the most important programming languages in the history of computer science, still in use today. He coined the term time sharing for the computing architecture that allowed multiple users to use a single computer simultaneously. He remained a central figure in AI research until his death in 2011. Marvin Minsky, who co-organized Dartmouth, became the director of the MIT Artificial Intelligence Laboratory, one of the most important research centers in the field. He wrote influential books. He built perceptrons, early neural network hardware. He argued, with characteristic directness, that the brain was a machine and would eventually be understood as such. He was also wrong about something important. He was wrong in a way that set the field back for decades. Before we follow the path that Minsky got wrong, let us pause and name some people who tend not to appear in the standard history of artificial intelligence. Grace Hopper was a Navy Rear Admiral and computer scientist who developed the first compiler, the program that translates human-readable code into machine-executable instructions. Every programming language that has ever been used to write AI software runs on the principle that Hopper established. She is sometimes called the mother of computing. She is rarely called the mother of AI, but she is foundational to everything that made it possible. Ida Rhodes, working at the National Bureau of Standards in the 1950s, developed some of the first programming techniques for early computers and contributed to the development of the COBOL programming language. Her name is almost entirely absent from popular histories. Mary Lee Woods worked on the Manchester Mark I, one of the first stored program computers, at the University of Manchester in the late 1940s, writing software and contributing to debugging techniques at a time when computer programming was so new that the word programming had not yet been fully standardized.
Vera Molnar,
a Hungarian-French artist, was using computer programs to generate visual art in the early 1960s, before almost anyone else had thought to use computing as a creative medium. Her work anticipates generative AI by 60 years. And then there is Valentina Tereshkova and Olga Ladizhenskaya and Rozsa Peter, mathematicians whose work on formal language theory, recursive functions, and computability laid theoretical foundations that AI researchers would use without always knowing whose work they were building on. The history of AI, like every history in this series, is substantially the history of people whose names were not kept. In 1957, a psychologist named Frank Rosenblatt at the Cornell Aeronautical Laboratory built something he called the perceptron. The perceptron was a machine, actual hardware, not just a theoretical design, that could learn to recognize patterns. It consisted of a grid of light-sensitive cells connected through a weighted system of wires to output neurons. When shown images, it could adjust its weights, the connections between cells, to improve its pattern recognition over time.
Rosenblatt was not shy about the implications.
He gave press conferences. He told the New York Times that the perceptron might eventually be able to recognize people and call out their names, translate languages in real time, and write its own programs. The Navy, which had funded the research, described it in a press release as the embryo of an electronic computer that will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This was, by any fair assessment, wildly overstated. But the underlying idea that a machine could learn from examples rather than being explicitly programmed was genuinely important. In 1969, Marvin Minsky and Seymour Papert published a book called Perceptrons. The book was a rigorous mathematical analysis of the perceptron's capabilities, and it demonstrated that single-layer perceptrons could not solve a certain class of problems, specifically problems that were not linearly separable, including the simple logical operation called XOR.
The book was technically correct.
It was also interpreted by a significant portion of the AI research community as proving that neural networks were fundamentally limited, that the learning approach was a dead end. Research funding for neural networks dried up. The field entered what became known as the first AI winter, a period in which the gap between the promises of AI researchers and the actual capabilities of their systems became impossible to ignore. Funding agencies lost confidence, and the field contracted. It would not be the last winter. And the specific limitation that Minsky and Papert had identified, the inability to solve non-linear problems, would eventually be overcome. Not by proving them wrong about single-layer perceptrons, but by adding more layers. In the 1970s and 1980s, AI research largely abandoned the neural network approach and pursued a different strategy. Instead of trying to make machines learn, researchers tried to encode human knowledge explicitly.
Expert systems
were programs that contained, in the form of rules, the knowledge of domain experts, doctors, lawyers, geologists, engineers. Given a patient's symptoms, the system could reason through them using its medical knowledge base and produce a diagnosis. Given a geological survey, it could identify likely mineral deposits. These systems worked, in limited domains, remarkably well. Mycin, developed at Stanford in the early 1970s, could diagnose bacterial infections and recommend antibiotic treatments with accuracy comparable to specialist physicians. XCON, developed for Digital Equipment Corporation, saved the company tens of millions of dollars annually by configuring computer systems for customers. Expert systems became a significant commercial industry. The Japanese government launched the fifth-generation computer systems project in 1982, a 10-year, $500 million initiative to develop the next generation of AI-powered computers. American and British governments launched competing programs in response. None of them produced what they promised. The fundamental problem with expert systems was the knowledge acquisition bottleneck. Encoding the knowledge of an expert into a rule-based system required extensive interviews with the expert, painstaking translation of their knowledge into formal rules, and constant maintenance as knowledge changed. And the systems were brittle. They could not handle situations their rules had not anticipated, could not learn from new examples, could not generalize from what they knew. Real intelligence, it turned out, was not just a large collection of rules. It was something else. By the late 1980s and early 1990s, the expert systems bubble had burst. Funding collapsed again. The second AI winter set in. The pattern, exaggerated expectations, apparent breakthrough, commercial disappointment, funding collapse, had now occurred twice. Some people began to wonder whether it was a permanent feature of the field rather than a temporary setback.
They were wrong.
But they were not unreasonably wrong. While expert systems were rising and falling, a small group of researchers had continued to work on neural networks. They had been largely ignored during the AI winter, working in relative obscurity with limited funding, pursuing an idea that the mainstream had largely written off. The key breakthrough came in 1986, when David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper demonstrating a practical algorithm for training multi-layer neural networks. The algorithm was called backpropagation, a method for efficiently calculating how to adjust the weights in a network to reduce its error on a given task. Backpropagation was not entirely new. Elements of it had been discovered independently by several people over the preceding years. But Rumelhart, Hinton, and Williams's formulation was clear, practical, and packaged in a way that made it usable by the broader research community. Multi-layer neural networks, networks with more than one layer of neurons between the input and the output, could in principle solve the XOR problem, and others like it that Minsky and Papert had shown were beyond single-layer networks. Adding layers added representational power. Deep networks, networks with many layers, could in principle represent extremely complex functions. But training deep networks required enormous amounts of data and enormous amounts of computation. In 1986, neither was available. The theoretical foundation had been laid, the hardware had not caught up. Geoffrey Hinton continued working on deep neural networks through the 1990s and 2000s, when they were unfashionable, when funding was difficult, when the mainstream had moved on to other approaches. He worked in Toronto, partly because Canadian funding agencies were somewhat more willing than American ones to support basic research in areas without obvious commercial application. He is now known as one of the godfathers of deep learning. He shared the 2024 Nobel Prize in Physics with John Hopfield for their foundational work on artificial neural networks. He resigned from Google in 2023 to be able to speak freely about what he thought AI was becoming. His concerns were not about the past, they were about the future. In 2012, a team led by Hinton's graduate student, Alex Krzyzewski, entered an image recognition competition called ImageNet.
The competition required identifying objects in photographs.
Cats, dogs, chairs, kettles, thousands of categories. The best systems in previous years had achieved error rates of around 25 to 26%. Krzyzewski's system, AlexNet, a deep convolutional neural network trained on a graphics processing unit, achieved an error rate of 15.3%. The margin of improvement was shocking, not incremental, transformative. The field understood immediately that something fundamental had changed. The change was not conceptual. The ideas behind deep neural networks had been known for decades. The change was computational. Graphics processing units, developed for rendering video games, turned out to be extremely well suited for the matrix calculations required to train neural networks. And the data was now available. The internet had produced datasets of text, images, and video at a scale that would have been unimaginable a decade earlier. Over the following decade, deep learning transformed every field it touched. Computer vision, speech recognition, machine translation, drug discovery, protein structure prediction, DeepMind's AlphaFold system, which predicted the three-dimensional structure of proteins from their amino acid sequences, solved a 50-year problem in biology and was described as one of the most significant scientific achievements of the century.
The patterns Minsky had believed
Were fundamentally impossible for learning machines turned out to be learnable, given enough data and enough computation. Minsky had died in January 2016. AlexNet's success had been in 2012. He lived to see the beginning of the revolution, but not its flowering. In 2017, researchers at Google published a paper with a title that has become one of the most cited in the history of computer science. The title was, "Attention is All You Need." The paper introduced a neural network architecture called the transformer. The transformer was designed for sequence processing, taking a sequence of inputs, like the words in a sentence, and producing a sequence of outputs, like a translation, into another language. The key innovation was the attention mechanism, a method that allowed the network to focus on different parts of the input sequence when producing each part of the output.
the transformer architecture was more efficient to train
Than previous sequence models, scaled better with increasing amounts of data and computation, and produced qualitatively better results. Within a few years, it had become the dominant architecture for natural language processing. The insight that drove the large language models, GPT, BERT, Claude, Gemini, and their successors, was that if you trained a transformer on enough text, it would learn to represent language in a way that was useful for almost any language task. Pre-training on a vast corpus, then fine-tuning for specific applications. GPT-3, released by OpenAI in 2020, had 175 billion parameters, the adjustable weights in the network. It could write essays, answer questions, complete code, translate languages, and perform tasks it had never been explicitly trained for. The emergence of capabilities from scale, the discovery that making a model larger and training it on more data produced qualitative improvements rather than just quantitative ones, surprised even the researchers who built it.
In November 2022,
OpenAI released ChatGPT, a version of GPT 3.5, packaged as a conversational interface that anyone could use. It reached 1 million users in 5 days. It reached 100 million users in 2 months. No consumer technology in history had been adopted so quickly. The public had discovered AI. The researchers who had been working on it for 60 years watched. Let me try to say what the large language models are and what they are not, as precisely as current understanding allows. They are, at a technical level, very large neural networks trained to predict the next token in a sequence. They are trained on enormous amounts of text, a significant fraction of the text that human beings have produced and put online. During training, they adjust billions of parameters to become better at the prediction task. What they learn in the process is something. Not just statistics, not just the word is often follows the word sky. They learn representations of the world, internal encodings of concepts, relationships, facts, reasoning patterns that are encoded in the activations of their neurons in ways that researchers are only beginning to understand.
What they do not have,
as far as current scientific understanding can determine, is consciousness, subjective experience, or the kind of understanding that humans have when they genuinely know something. They are very good at producing text that resembles the output of a thinking being. Whether that resemblance indicates that they are, in some sense, thinking is one of the most contested questions in contemporary science and philosophy. This is not a political question, it is a scientific one, and science does not yet have a definitive answer. What they can do is remarkable. They can explain complex concepts clearly, they can write code, they can diagnose medical conditions from descriptions of symptoms. They can translate between languages with a fluency that approaches, and in some cases, exceeds, human professional translators. They can generate convincing images, music, and video. They can solve mathematical problems. They can write poetry.
what they cannot do reliably.
Consistently reason about situations they have not encountered in training. Ground their outputs in verified facts without supplementary tools. Know when they do not know something. The hallucination problem, the tendency to produce confident-sounding text that is factually wrong, is a genuine and unsolved issue. Turing asked his question in 1950. He said he believed that by the year 2000, computers would be capable of passing his test, of producing responses that a human interrogator could not reliably distinguish from a human's. He was roughly correct on the timeline, though the test itself has turned out to be less useful than he imagined. Passing the Turing test has turned out to be achievable without the systems necessarily having the kind of intelligence the test was designed to probe. The deeper question, the one behind the test, the one that Turing's 1950 paper was really asking, has not been answered. Can machines think? Not simulate thinking, not produce outputs that look like the products of thinking. Think, in whatever sense the word means, when we apply it to ourselves. The honest answer, in 2025, is we do not know. Not because the question is unanswerable in principle, but because we do not have a sufficiently clear understanding of what thinking is in humans to be able to say whether the systems we have built do it or only resemble it. The hard problem of consciousness, the question of why physical processes give rise to subjective experience at all, remains unsolved. Without solving it, the question of whether an AI system is conscious is, in a precise sense, unanswerable. Geoffrey Hinton, who spent his career building the systems that now underlie almost all modern AI, said after leaving Google that he was genuinely uncertain about whether the systems he helped create had something like experience. He was not claiming they did. He was saying he could no longer be confident they did not. This uncertainty, coming from the person whose work made modern AI possible, is not alarmism. It is intellectual honesty about the limits of current understanding. Before we arrive at the question this series has been building toward, let us name some of the people whose work built AI and who tend not to appear in the histories written during moments of excitement. Fei-Fei Li created ImageNet, the massive labeled image dataset that made the 2012 deep learning revolution possible. AlexNet's breakthrough happened on her dataset. She is sometimes called the godmother of AI, but her contribution, the years of painstaking labor required to assemble and label 14 million images, is less celebrated than the algorithms that ran on it. The data, as she has pointed out, is half the story. Timnit Gebru, a computer scientist who studied bias in AI systems, co-authored a paper examining the risks of large language models that her employer Google asked her to withdraw. When she refused, she was fired, or left, depending on which account you accept. The paper raised concerns that the field is still grappling with. Her departure from Google attracted significant attention and contributed to ongoing debates about ethics in AI research. Joy Buolamwini, a researcher at the MIT Media Lab, demonstrated that facial recognition systems, AI systems used for surveillance, identification, and law enforcement, performed significantly worse on dark-skinned faces than on light-skinned ones, and significantly worse on women than on men. Her work, published in 2018, triggered legislative responses in multiple countries and a reassessment of how AI systems were being deployed in high-stakes contexts. Yoshua Bengio, who shared the 2018 Turing Award with Hinton and Yann LeCun for their work on deep learning, has become one of the most prominent advocates for careful, safety-focused AI development. His position has evolved as the systems he helped create have grown more capable. These are not peripheral figures. They are part of the story of what AI is and what it might become. The history of AI, like the history of every technology in this series, is wider than its famous names. We have now traveled in this series through the history of electricity and the light bulb, through the radio and the telephone, through the computer and the internet, through DNA and penicillin and vaccines, through the atom and gravity and time and nuclear energy, through the printing press and the steam engine and the camera and the moon. In every episode, the story has had the same structure. The invention was not what you thought. The person who gets the credit was not alone. The person who did the foundational work was often forgotten. The technology changed more than anyone anticipated and cost more than anyone wanted to acknowledge. Artificial intelligence is the same story, and it isn't. It is the same story because the history of how we got here is full of forgotten names, misattributed credits, decades of ideas that were right but arrived before the hardware was ready, cycles of hype and disappointment, and eventual vindication. It is not the same story because, unlike electricity or the printing press or the steam engine, the thing we have built this time might eventually be able to do something that no previous technology could do.
It might be able to think.
Or it might only appear to think in a very convincing way, while being something quite different from what we mean when we use that word. We do not know yet which of these is true. Every other technology in this series had a moment when the question was settled. The light bulb either stayed on or it didn't. The telephone either transmitted a voice or it didn't. The moon landing either happened or it didn't. The question Turing asked has not yet been settled. He asked it in 1950. He was using it to probe the nature of intelligence, of mind, of what it means to think. He was not primarily worried about a future in which the machines became more intelligent than the people who built them. He was asking a philosophical question. 75 years later, the question is still philosophical, but it is also practical. The systems now exist. They are doing things. They are in hospitals and courtrooms and schools and newsrooms. They are helping design drugs and predicting protein structures and writing code and generating images of things that never existed. And at the edge of the ability to describe what they are, at the frontier where the engineers and the philosophers and the neuroscientists and the ethicists are all standing looking at the same thing from different angles, not yet certain what they are seeing. The question remains open. Can machines think? We built something. We do not yet know what it is.